Thank you for joining me today. My name is Charles Poe, and I'm excited to talk about how GPUs are transforming the way we approach computational tasks. The title of my presentation is Unleashing GPU's Power, Accelerating Linear Algebra, Simulations, and more. Over the next 20 minutes, we will explore how GPU revolutionized performance in key areas like linear algebra and simulations. Let's dive in. The world is drowning in data. Neural networks contain hundreds of billions of parameters, demanding trillions of floating point operations. Financial institutions analyze millions of transactions per second for real-time risk assessment. And scientific instruments produce terabytes of experimental data daily. Traditional CPU with a 6 to 64 core were designed for sequential tasks. They excel at complex logic but struggle with massive parallel workload. Memory bandwidth limitations create bottlenecks, and data cannot flow fast enough to reach computational core. As a result, computational tasks and simulations take days instead of hours. Enter the GPU era, a computational revolution born from video games. Introduced in the 1990s, GPUs were designed for one purpose: rendering pixels for video games. A simple frame requires millions of independent calculations, perfect for parallel processing. By 2006, researchers realized this massive parallelism could accelerate scientific computing. NVIDIA launched CUDA, and the general-purpose GPU era began. Modern GPU pack thousands of cores, 10 to 20 times more memory bandwidth than CPUs, with optimized architecture for thousands of simultaneous operations. What once took CPUs close to a week now complete on a single GPU in hours. Matrix multiplications, fundamental to machine learning, run 100 times faster. Fourier transform for signal processing accelerate by 50 times. The question is no longer whether to use GPUs, it's how to harness them effectively for your computational task. Our agenda includes 4 topics. The first, GPU versus CPU, a paradigm shift, where we will look at the fundamental difference between CPUs and GPUs, and when GPUs are better suited for computational tasks. Second, the foundation of GPU computing, where we'll dive into the framework in the Wolfram Language that make it possible to take advantage of GPUs. Third, accelerated linear algebra, focusing on how GPUs are used for linear algebra operations in the Wolfram Language. Finally, simulation and more, where we look at examples from simulating complex dynamic to fast in high-resolution image of a Mandelbrot set. To understand why GPU excels at modern computational tasks, let's compare the architecture to CPUs. CPUs are designed with a few powerful cores, typically 8 to 64, optimized for sequential processing. They handle complex logic efficiently. In contrast, a modern GPU has thousands of cores. NVIDIA H100 has 16,000 cores, while Apple M4 Max integrates 40 GPU cores with unified memory. These cores are simpler than CPU cores, but are designed to execute thousands of threads simultaneously. This makes GPU ideal for repetitive, data-intense tasks like matrix multiplication and simulations. Additionally, GPU feature high memory bandwidth, up to 4 TB per second, allowing them to process large datasets more efficiently. While CPU minimizes latency for simple operations, GPU maximizes throughput for thousands of operations. GPUs are not always the best choice for every workload. but they shine when embracing parallelism is key. Let's explore when it's suitable to use a GPU. Massive data parallelism. If your workload involves performing the same operation on large datasets, such as matrix multiplications or image processing, GPUs are ideal. Their thousands of cores can process data in parallel, significantly reduce computational time. High computational intensity. Tasks that require a large number of floating point operations, like running numerical simulation, benefit greatly from GPU specialized hardware. Iterative algorithm. Workflows which involve running the same computation many times with slight modification are well suited for GPU due to their ability to handle repetitive tasks efficiently. Memory bandwidth requirement. If your application needs to move large amounts of data quickly, such as in a scientific simulation or financial modeling, GPU provides significant high memory bandwidth compared to CPUs. Scalable workload. For a problem that can be divided into smaller, independent tasks, GPU allow you to scale computation across thousands of threads, making them perfect for distributed computing environment. However, it's important to note that GPUs are less effective for tasks that are inheritance sequential or require frequent branching. In such cases, GPU remain the best choice. The key is to identify workload with high degree of parallelism and computational intensity to leverage the power of GPUs. Modern computing systems are increasingly adopting an heterogeneous approach, leveraging the strength of both CPU and GPU to achieve optimal performance. Apple M4 Max, for example, come with 16-core CPUs and 14-core GPUs. In this model, the CPU acts as a host, orchestrating tasks and handling sequential or logical intensive operation. Meanwhile, the GPU serves as a device executing highly parallel, computer-intensive workload. The division of labor allows each processor to focus on what it does best. By combining the flexibility of CPU with the raw computational power of GPUs, we can achieve unprecedented performance and efficiency. Parallel programming models provide tools and abstraction needed to distribute workload across thousands of GPUs core efficiently. CUDA, developed by NVIDIA, is the most widely used framework for GPU programming, offering a rich set of libraries and APIs. Apple Meta Framework is designed for macOS and iOS devices, enabling high-performance graphics and compute tasks. High-level libraries abstract away the complexity of GPU programming, make it accessible to a broader audience. Domain-specific frameworks are often optimized solutions for specialized tasks like machine learning or molecular simulations. By leveraging this programming model, we unlock the full potential of GPUs in the Wolfram language. Introduced in 2008 at the early days of CUDA, CUDA Link provides seamless access to NVIDIA CUDA and handles the entire process of compiling and linking CUDA code, eliminating the need of manual setup. Advanced users can write custom CUDA kernel and execute them to CUDA Link. CUDA Link is being superseded by CUDA compiler tools. CUDA compiler tools in the Wolfram language extend the capability of the Wolfram compiler, enabling seamless integration with NVIDIA CUDA ecosystem. You can compile CUDA code directly within the Wolfram environment, leverage NVIDIA library for high-performance GPU computing. Key features include integration with the Wolfram compiler, access to NVIDIA library like cuBLAS and cuFFT, and GPU data management. Functions are available to load data into the GPU, retrieve results, and manage memory efficiently. Automatic memory management ensures that GPU memory is free when it's no longer needed. By combining the Wolfram language with NVIDIA CUDA, you can create high-performance GPU-accelerated applications with minimal overhead. GPUArray is a new feature in the Wolfram language that provides direct access to high-level tasks using GPUs. It represents GPU-accessible memory, making it seamlessly available to high-level functions without requiring you to write GPU-specific code. GPUArray abstracts the complexity of the GPU programming, allowing you to focus on your computation rather than the underlying hardware or implementation. It integrates seamlessly in the Wolfram language heterogeneous computing model, enabling efficient use of GPU and CPUs. It is designed to work across multiple GPU platforms, including NVIDIA, Apple Metal, and more, for portability and flexibility. By representing GPU-accessible memory and data in a high level, in a GPU-agnostic manner, we can harness the power of GPU for a wide range of functions and tasks in the Wolfram language. Let's look at a sample example. How to compute the root mean square error. The root mean square error measures the average difference between a statistical model predicted value and the actual values. It's a key metric for assessing the accuracy of regressions and other statistical models. To compute the root mean square error, you compute the residual of each observation, square each residual, sum all the square residual, and divide them by the number of observations, and take the square root of the result. The traditional calculation does not scale well for large data sets. We can leverage GPU capability to significantly improve the performance by transferring the data to the GPU using GPU arrays. This coincides with the implemented functionality in the system. The performance can be further enhanced by compiling the code for a specific GPU, enabling faster and more scalable computations. The performance can be further enhanced by compiling the code for a specific GPUs, enabling faster and more scalable computations. Here is a performance comparison. GPU-based approximations are faster than their non-GPU counterpart. Compiled GPU versions not only outperform others, but they also scale effectively with data size, making them ideal for large-scale problems. Linear algebra operations such as matrix and vector computation are at the heart of many scientific and engineering applications. These operations are effectively suited for GPU massively parallel architecture, enabling unprecedented parallel and scalability. Massive parallelism. GPUs are designed to handle thousands of threads simultaneously, making them ideal for matrix multiplication, eigenvalue problem, and matrix decompositions. High memory bandwidth. Modern GPU offers significantly high memory bandwidth compared to CPUs. This is critical for memory-intensive linear algebra tasks. Optimized libraries. Libraries such as cuBLAS, QSolve, and Magma provide high optimized implementation of linear algebra routines, leveraging the full potential of GPU hardware. These libraries are now integrated in the Wolfram language, making GPU's acceleration accessible to users. Fundamental vector and matrix operations are supported. Basic operations include element-wise addition, subtraction, multiplication, division, as well as scalar operations like scaling a vector or a matrix by a constant. GPUs are used to accelerate matrix multiplication, transpose, inverse, and decomposition such as LU, QR, and SVD. These linear algebra operations achieve remarkable performance improvement by dynamically and efficiently balancing the workload between CPU and GPU and avoid data transfer bottlenecks that are frequently present in numerical algorithms. Now, here are some computationally intensive simulations that are easily implemented using GPUArray. So here we have a fast high-resolution image of the Madepro set. Here are some compute-intensive simulations that are easily implemented using GPUArray. This is a fast high-resolution image of the Madepro set. Here, we simulate complex dynamic with continuous serial automata. Many more GPU examples are available in the Wolfram Language example repository. As we wrap up, let's quickly summarize the key ideas from today's talk. First, the Wolfram Language provides tools to solve high-level tasks, allowing us to focus on what we want to compute rather than how it's computed. GPUArray abstracts away GPU programming complexity. With this high-level abstraction layer, you don't need to write low-level CUDA code or GPU code. Instead, you express problems symbolically and the Wolfram language efficiently maps them to GPU execution when appropriate. Third, the framework embraces heterogeneous computing, balancing load seamlessly between CPU and GPU. This ensures that we can leverage the best of both worlds, the CPU flexibility and the GPU parallel processing power. Fourth, we explore the idea of CPU-GPU agnostic design. The same function and code base automatically work on CPU, GPU independently of the platform, CUDA, Apple, Metal, or any other. Fifth, whether you are working with machine learning, image processing, numeric computation, GPUArray functionality is available. And finally, all these elements come together to deliver optimal performance and flexibility, all in a single and elegant workflow. Thank you for your attention. Okay, thank you all. So I'm ready to take questions. Let's see here, share my screen. So I'll first go with a few questions I have on the chat here. So the first question from Andrew is, how can I verify whether my Wolfram Mathematica is leveraging GPU on Apple M series, right? And if not, what does Wolfram recommend on the macOS computer intensive Wolfram language workload? Well, in principle, we support, not in principle, we support Apple series, at least macOS 13.3. And the easiest way for you to do that is essentially to do GPUArray of an array, like in this case, it will load, and if you actually get GPUArray back, that means it's working. So it's as simple as that, right? And the same will also happen on your NVIDIA, right? So as you saw at the beginning, we kind of automatically check if your driver and everything is compatible, and if everything is in place, then we return you the GPUArray we created. selected. So that's one way. Or that's the way actually. So it kind of works seamlessly like any other function in the system. So the next question is there experimental GPU support of tabular? Not at this time, right? So tabular is still fresh, but we hope as we continue, improving part of the system and accelerating computation, GPUArray will be supported in tabular or other part of the system. And let's not forget that in long term, right, what we hope is that, you don't really have to invoke directly GPUArray. If you call an algorithm, you'll automatically call GPU or use whatever resource you have in your machine, right? And actually one example, a good example is the new linear algebra operation we're introducing in the coming version, right? For example, linear solve will probably, will take advantage of that depending on the size of your matrix. And if you decide maybe to say target GPU, or you call GPUArray, then we can use actually that behind the scene, or those hybrid methods. Okay, next question is from Michael. So macOS doesn't support NVIDIA driver. Any workaround? As far as I know, no, unless you decide to use, cloud GPU, but you cannot directly use a NVIDIA card on Mac, at least the M series at this time. Another question of Michael. Apple Computer doesn't support GPU from NVIDIA. Is there anything macOS user can do? As I pointed out, I think the easiest solution now, if you really want to program and use your Apple, is just to use a cloud GPU, CUDA GPUs. Next question, can you please update profiling and system benchmark to show performance gain from using GPU core on Mac? That's a great suggestion. Actually, we are working on the benchmark. As you notice in the earlier version, we introduced, we updated the benchmark. Now we have a function, system benchmark, which actually run and, benchmark your system. So we are updating it. And, the hope is that very soon you'll actually be able to take into account the GPU you have on your machine, as well as running specific tests like for image processing, signal processing, or linear algebra, depending on what you want. So it's coming. We are working hard on trying to push that. So we'll have a series of benchmark depending on different area and domains. But if you go to the main page of GPU computing, so we kind of have the list of functions and area which, can use GPUArray. So from array, linear algebra, Fourier, random number generation, discrete statistic and other statistic, mathematical function, visualizations, obviously the compiler, which GPUArray is built on top of the compiler. And also at the end, we have these two pages, which is Apple GPU and NVIDIA GPUs. So those pages actually specialize to only the one which are currently supported. As you can imagine, there is a difference, and we are working hard to kind of keep them the same, but there's a difference between what we support on Apple and on CUDA, right? But we try to kind of make sure that, most of your code work nicely on both systems. So you can take a look at those and, see which functionality work on your hardware. Okay. Next question from Enrique. Does GPUArray work with Intel Iris GPU? Not at this time. So that's something we actually, working on. As I discussed during the talk, we try to make the code GPU agnostic, the same as we have been doing in the system with CPU, right? You never worry what type of CPU is running on your machine. We just work on that. So currently we are working hard on extending the support beyond CUDA and Apple, right? So we hope we are going to get to AMD and probably Intel next. Right? So it's work in progress. Stay tuned and keep sending us the suggestion and what you hope or you want to see, and we work hard on adding that in the system. Okay, so that's the list of questions right now I see in the live Q&A. So I'll hang out a few minutes and see if there's any more question and from there. Well, I think that's most of the question, and and if you have any more question, if something comes to your mind, don't hesitate. We have a office hour, I think Friday at around 1 p.m. So I will be there as well as the whole discrete computational team to answer your question, right? If it's GPUArray, geometry, graph, number theory, and any other area, don't hesitate to come, as well as to contact us directly here to chat. Okay. So thank you for your time and have a good rest of your conference.